Niayesh, sorry, Afshordi. Professor Afshordi obtained his PhD in astrophysical sciences from Princeton University in 2004. And he's currently working at University of Waterloo and at the Perimeter Institute. Today, he will talk about a novel predictive framework for the novel coronavirus. So please, Dr. Afshordi, if you can share your screen.
Definitely. So let me just find share.
You should be able. Okay, that's great.
Okay. Okay. Let me just give me a second. I think maybe it might be a bit better if I just share one screen. But yeah. Okay. So let's just this one. Okay. So do you see this now? Or not?
We're able to see. Thank you so
yeah,
much.
we can see your screen.
Okay, wonderful. Okay, well, thank you very much for the invitation and for coming on board and for having me. It's my pleasure to be able to talk here to epidemiologists. As the wonderful introduction Elena and Jude mentioned, I'm an astrophysicist. But as this pandemic hit, like all of us, it's something that affects all of us. And hopefully I can try to convince you throughout this that we can all contribute to solving this big problem, because we all have different backgrounds, diverse different backgrounds and different expertise that could help address the issues. So, so this is, before we get into it, is a list of the collaborators. Ben Holder, who is actually online here, from Grand Valley State University, although he does spend a lot of time in Toronto. Then there's Matt Barhami and Danny Lisplau from Wolfram Research Institute, which is in the US. And then more recently, Steve Weinstein, who's in philosophy at University of Waterloo, and Beth Gould, who's at Queen's University, have started working with us in this project. And if you want to explore further beyond what you hear during this talk, we have an online dashboard that's linked here. You can go to my homepage with lots of information. There is our first paper and hopefully many more to come that you could find online on our archive and medRxiv. And then if you do go to our dashboard, this is how it looks like. This is what I'm showing you is for the United States now. And it does tell you, based on basically our best fit model to the epidemic, how historical predictions would work in the US and how different mitigation strategies in different counties could work out into the future. And we give basically all the information that's relevant to epidemic and its modeling in each US county. So if you do live in the US or are interested, this is the place that you want to look at. Now, I am not in the US. Yeah, those of you listening could be joining in from different places in the world, but I'm in Canada. And of course, the question is, what about Canada? Why isn't that here? Unfortunately, the type of data that we needed, this hasn't been available until recently. In Canada, and there is basically some help. We haven't had enough basically help and time to implement a Canadian dashboard. But this is something that can be done for Canada and can be done for all other countries in the world, but it requires local expertise and lots of data, which does take time to get. But why am I talking to you in Center for Disease Modeling? What I actually do for a living is thinking about the Big Bang, about how quanta gravitate, the dark universe, dark matter, dark energy, gravitational waves, and black holes. And these are some of the pictures from papers that I've written. But then, of course, as we heard, when the pandemic hit, we were all in this together. So, and that's really the main reason why I am talking to you, that we are all going through this together. And we're all expressing the same hardships, some more than others, And we have to try to deal with this, this issue that has been impacting all of our lives across the board. And we all have our own diverse backgrounds and complementary techniques and expertise and approaches to problems. And like any hard problem that you have to try to tackle it any way that you can, having more ways of attacking a problem is always better, because one of them may work better or more may work. In particular, the reason that I thought I could contribute to this, my group and I, is that my own expertise has been in, at least when I did my PhD at Princeton, I looked at how you could look at correlations between the light, the microwave light that comes from the Big Bang, and galaxies that we see in the sky. If we can look at actually a statistical correlations between these and learn about the dark components of our universe, what I call the other 99%, which includes dark matter, dark energy, and invisible matter, plasma or atoms, ionized atoms that fill the universe. And these are not visible on their own, but if you actually use these statistical correlations that have to be carefully defined, you can actually learn about the evidence for all these dark components of the universe. Similar is the case of the coronavirus that is affecting our lives. We cannot see it directly, or very, very difficult to see it directly, except for very special circumstances. But nevertheless, it is spread throughout the world and it affects us in very visible ways. And we have to use visible signatures like infections and mortalities and other symptoms to track where it's coming from, very much like the way we track dark matter and dark energy. So maybe this is a type of complementary technique and approach that can be used to help this, our global battle. More specific questions are, what factors could drive the epidemic growth or decay? Can a study of diverse epidemics in terms of demographics, settlement, weather, and other factors allow these factors to be identified and distinguished? Now, we can find correlations, but that doesn't necessarily mean causation. So that's a harder question. And for that, we need a mechanistic or a causal model to address causation. One of the most sticky questions that we've been dealing with for the past 6 months is the issue of herd immunity. And we're hoping that a real causal mechanistic model could address that if it actually explains the data. And then, of course, the other important question is, what should we do? What are the best steps we should take, or wisest steps we can take to manage or manage epidemic or future outbreaks? Another way of simplifying this question is that these two places, the Manhattan Island in New York or Kodiak Island in Alaska, do they have to both go into lockdown when the pandemic hits? And this is a question about this pandemic and about pandemics to come that you could, every person, every citizen who lives anywhere in the world could ask that question. And that's the question that we want to answer. So, so this is what's about to come. So we we embarked upon building a novel predictive framework, complementing other models of epidemiology for COVID. What is special about our model is that we actually used observed tracers of transmission, that's social mobility from cell phone activities, face mask use based on people's Google searches and social distancing, weather based on historical weather and upcoming weather forecasts, population density and sparsity, demographics, and immunity. So these are things that can be traced based on observations or based on the data that we have available. These are external tracers. So these are not internal to the model. And then we have model for incubation that is similar to the standard compartmental models, but we also have alternatives to them that might probe other possibilities. So our novel predictive framework combines these external tracers of transmission with a model of incubation. And at the end, we're asking that can we have a universal model with something of order 10 parameters that fits all epidemics, 500 and plus US epidemics over the last 6 months. So that's roughly more than 8,000 data points. And can that model be used to predict them into the future, depending on the mitigation strategy? So this is what's unique about the model, because we are trying to fit all the epidemics at once with the same parameters. And to facilitate that, we use these external informations that specify what's different from one community to another, and what's different from one time to another. So namely, various measures of mobility and human interaction and weather and population density. Now, this is in contrast to the toy models that are often used, but they don't actually fit data, or the forecasts that are often used, and they're famous forecasts that all they simply do is they extrapolate past behavior of each epidemic or each place into the future, but doesn't really connect one epidemic to another epidemic. So our model or our approach is try to explain all of them, at least within the US, where there is some homogeneous information available, try to explain all of them at once with the same parameters. So with that introduction, this is the outline. I'm going to tell you about the data that we will use. I'm going to tell you a little bit about linear models, about the nonlinear models, or mechanistic models, about herd immunity and what we know and what we don't know about it. And finally, about how we can put all this information together and try to manage a pandemic. So let's start with the data. So the largest epidemic data set that's available is that of the United States, south of our border here in Canada. So some of this data set are, of course, that of COVID, which, as we know, is over 200,000 mortality and millions of cases that have been detected. But let's just start with the static data set. So the important thing about the static data set is, of course, virus is transmitted from person to person. So if we know what demographic a population has and how many people you have in every geographical pixel, then that actually tells you, or that can help you predict how often transmission happens from person to person. So we use demographic data from US Census, and we use weighted population density that I'm going to introduce in the next slide. And what I call PWD, which comes from the GSS population raster image produced by the European Union. And we use a novel measure called population sparsity that tells you about the sparsity of population in a county. And we use dynamical data. So the dynamical data is daily mortality and case incidence from Johns Hopkins University and New York Times. We use weather information, temperature and humidity from NOAA. And we use human mobility that's been reported by Google for various US counties in workplace, home, and transit, which are measures of how much people basically interact with each other, or the measures of lockdown in reverse. And most recently, this is something that we started doing in the last couple of months. We now have measures of mask use by calibrating the Google Trends searches for face masks against surveys of face masks. So maybe if there is one thing that you want to take away from this talk is the role of population weighted density, which is not often appreciated in epidemiology. Although it's something that everybody talks about, of course, population density is important. Rural Manitoba and downtown Toronto won't have the same kind of epidemics, neither do New York City and Nebraska. But the difference is population density, but it's not exactly the population density that you can look up on Google. There is a more nuanced version of population density called lived density or population weighted density that people have been really talking about for the past 10 years or so, because this data on it has not really been available until recently. So what it is the average density of people in parcels of a given area. The highest resolution we have is 250 meters square pixels or parcels. However, what you do is that if you have a county made out of all these small parcels or pixels, you weight the density of each parcel by the number of people within that parcel. So this way, if there are a lot of empty places, they don't actually contribute to the population weighted density, even though the naive density would go lower if you have all these empty places. So you have a county or the geographical region with lots of deserts or seas, since nobody lives there, that shouldn't really matter for the density that contributes to an epidemic. It's only the lived density that matters. So example are these two counties. On the left, you have a more dense county. On the right, you have less densely populated county. However, if you look at population weighted density, they are the same, because where the people live, there's the same density of people, and all these empty places that nobody lives, that doesn't matter for population weighted density. So that's a measure that we are going to use, and it turns out to be the most important predictor of how fast an epidemic would grow. Another interesting factor that we introduced for our work as a novel measure, and in fact, it's inspired by something that Jim Peebles did. If you don't know, Jim Peebles won the Nobel Prize in Physics last year. Is a Canadian cosmologist, one of my old professors at Princeton. And one of his claims to fame has been to measure this so-called power, or what I call population sparsity, but he called it something else. He measured in the 70s for galaxy distributions in the universe. Now, we kind of borrowed the same prescription from Jim Peebles and applied it to people distribution. So, and the way you do it is that you basically look at this population weighted density and ask how that changes if you look at bigger areas, parcels of bigger and bigger area. So if you have a uniform distribution of people, then it doesn't matter on what scale you look at, population weighted density is always the same. So this gamma would be 0. If you look at a distribution like this, where there are some empty places, if you look at bigger area, you see that population weighted density becomes smaller. And if you look at the area of the entire county, which is the whole rectangle, then the area is the population weighted density is the naive density of that county. So so for this particular case, gamma is 1/3. And Peebles did this for the universe, and he found the gamma of 2/3 for the distribution of galaxies. If instead of the area, you have the volume, because of course galaxies live in 3 dimensions, people live in 2 dimensions on the surface of Earth. So, so that's not it. That also turns out to be important, because the more sparse the community is, the more slowly the epidemic would spread, even though they might have the same population weighted density. Because here, for example, on the left, the epidemic could grow in all directions, but if you have a sparser community, it has a harder time. The virus has a harder time getting from one side of the county to the other side of the county. And we're going to see this. So equipped with, so these are this kind of a static measures we use, and then we use dynamical measures. So for example, the top is the mobility that's been reported by Google, and we have, of course, data all the way up until last week on this. This is what we used originally for the early epidemic. And for example, you see in New York City, the mobility was at its normal, which is 0, it's a baseline. And sometime around March, so this starts from 29th of February. So this would be around 20th of March. That's when the lockdown started everywhere in North America. So you have this sudden drop in mobility with a slow gradual rise. Of course, nowhere is really back to normal, but you originally had something like a 70% drop in mobility. Basically, people weren't going to work, weren't going to grocery stores, weren't going anywhere, basically. But then that slowly started to recover. That wasn't the same everywhere. Los Angeles had a much less of a shutdown or a lockdown, even though the rules might have been the same. Just people were not as worried for reasons that we may not understand. Maybe because the epidemic wasn't as severe, maybe just because the local laws were not as severe. But the lockdown there was 50%. And in New York City, it went down to almost 75%. In Grand Rapids, Michigan, where my collaborator lives, that's also close to 50%. Then you have the case growth that was almost exponential early on and peaked at some point. Some of them flattened. And then there are second waves that we're going to talk about. Some of them have started to decline. And then we also use the weather data. So, what is the idea here? So the idea is that we want to identify what are the local drivers of epidemic transmission. Right? So as anybody who's done the statistics knows, the first weapon that you have when you look at correlations is regression. If you want to figure out what's important, you do a regression fit, which is the simplest, but often most effective way of doing this, although it doesn't always give you the right answers. And this is what we first did with the early epidemic, where we think that early on, the mitigations might not have been as important. Of course, that's not exactly true. So there is an exponential growth rate of the epidemic, this lambda, that you saw here is how fast the slope in the log of the number of cases as a function of time. So the lambda, you could measure it for these different metropolitan areas that we did for the early epidemic and see how it's correlated with various factors, this average mobility, log of the population weighted density, the specific humidity, the population sparsity, and with the median age of the community. And we see so there's of course a constant baseline, but if you see that the most important impact you see is in fact that of the lockdown. As soon as the lockdown started, basically the lambda, actually in this case, the places that had an earlier lockdown and a harder lockdown, they had a slower epidemic growth, and the places that had a later lockdown or less of a severe lockdown, they had a faster growth. But of course, this is not the only thing that matters. There is also population weighted density that is around 5 sigma significant. That means that's also very important. And then there are other factors that were important, but you couldn't see very well. The older population had the faster growth. The sparser population had a slower growth. And then there is, of course, weather, which is important. And these are all important at the same time. So if you just look at one factor, then you're going to confuse these various things happening. But if you try to fit for all of them simultaneously, you can actually identify them if you use a lot of data from various diverse epidemics. Now, we extended this beyond the early epidemic. And to do that, we had to kind of include more effects. So what we did was that you basically use the time-dependent exponential growth rate, which is basically the slope of the daily mortality as a function of time. So we do it over 14-day periods so that you could get basically bring down the noise. So at every point in the epidemic of every county, there is a slope that you could measure. We only use mortality statistics because it's less dependent on the, it does trace the incidence growth rate with some delay, but it's not dependent on testing rates and bottlenecks that we know have been impacting the testing, at least in the early epidemic, but also the testing policies do keep varying. Like here in Ontario, we are familiar with the regular changes in testing policies. We used to have walk-in tests. Now we have to do appointments. They become more or less available over time. And these things affect the measurements. The mortality, we hope that is a more reliable statistics of the underlying epidemic. And up until now, we have, in fact, more than 8,000 measurements of this mortality growth rates across 500 US counties over time and space, basically. And we could do, again, repeat a linear regression to identify whether the most significant drivers. And then I'm going to tell you that we're going to use a nonlinear or mechanistic model, which is based on renewal equation, to find the nonlinear prediction for the growth. That's going to be more predictive, and that's what, in fact, we use on our dashboard. So this is a long table. You don't have to go through this, but we kind of try to cross out all the things that don't really matter, at least back in July. And so we looked at a bunch of things. Many of them didn't have a significant correlation. We found in this time-dependent mortality growth, we found the same factor that was important for the early care case growth, in particular social mobility, although the delay is a bit longer because we're talking about death here, we're not talking about the cases. It's the log of the population weighted density. It's the population sparsity, it's a specific humidity, and the median age. And because we are using more data now over more time, then we have much higher significance of these results. For example, we can say both social mobility 2 weeks prior to death and 4 weeks prior to death are significantly important at, say, 9 sigma, and both around 9 sigma and 8 sigma. So they're both important for the growth rate. However, we discovered 2 surprising new effects that, as far as we know, nobody else has seen, at least in the systematic way that we found here, is that there is, first of all, there is independent dependence on the death fraction of COVID in that community. And that's in fact the most significant dependence that we find at around minus 10 sigma. This is from back in July, last July. The significance has only grown by now. And also the other effect, which I'm not going to talk about, is the log of annual deaths. And I think this, we don't really understand this, but I think it has something to do with the coarse graining. Larger counties with larger annual death, things happen more slowly in them. So that could be a coarse graining or averaging effect. But this issue of the dependence and the negative dependence and death fraction, which is independent of all the other things, social mobility, and we're going to see the mask use as well, that's a very interesting effect that we're going to talk about later. Now, these are just correlations, but we also want to find what's actually causally important. And for that, we need a causal model, something that's predictive, not just a regression analysis. So for that, we do a nonlinear or mechanistic model, similar to SEI models, susceptible, exposed, infected, recovered models that have been popular in epidemiology. However, we kind of do a slightly more general version of this SIR, which is somewhat different. And it will become clear in a minute, but that's why we do this. But we could be we could have used a slightly more sophisticated version of SAR to do this. So what we do here is we kind of treat the disease as a continuous process. And we look at basically C, which is some measure of the disease. And where someone is exposed, you start at C equal to 0. And then you start a random walk here. So basically, this is the incubation period. And at some point, some people actually cross this threshold of becoming infectious. So the idea is that this is a stochastic incubation. And then at some point, at that point, they can infect other people. So that's kind of what makes it different from a standard SEI model, because you could have actually a back and forth. So you could have a random walk. Some exposed people never become infectious, others do. So it's a stochastic incubation process. And it gives you just a different generation interval distribution that the standard SCIR or other SCIR models do give you. But it turns out this model is simple enough that you could just solve these analytically, and they're closed form for all the basically all the functions, and we can actually solve renewal equation. If someone is interested, I can show you that as well. So what is it that we are doing? So we're talking about, so the most important thing to understand about the epidemic, and it's the same with a standard CIR model as it is with our model, is that we're modeling collision of people together, because that's how the virus transmits. So this is a cartoon of these susceptibles, exposed, and infectious people. And what I'm trying to do here is showing circles of different size, because different people have different cross sections, either because something internal to the virus, or it could be because of their mobility behaviors. I mean, some people are more talkative. They might interact with more people. Others are less talkative. And here you notice that there's an infectious person who, so you can look at this green circle in the bottom and the red circle in the top. And if I run this, you notice that the green circle at the bottom becomes a blue circle in the top. And that was true because of the interaction with one of these infectious individuals. So what we want to model is how often this is happening. So basically the rate of new infections per time per area, which should be basically the number density of susceptibles times the number density of infected times an interaction rate. This is what's commonly known as beta. And in physics, this would be something like a cross-section times the relative velocity. However, the idea then is that this is 0 if someone is exposed but not infectious. So early on, when someone is exposed, they're not infectious yet. But then when they do become infectious, if they do become infectious, then the beta becomes a constant. So this is basically in one way of understanding the standard SCR model, but in terms of the interaction of people with each other. So again, I can tell you about the Renal equation if you're interested. So what this model tells you is a formula that relates the exponential growth rate to the decay rate, which is basically a rate of recovery or quarantine, the rate of the infection rate or the interaction rate of susceptibles and infected individuals, the susceptible density, and the diffusion time or the incubation time, or this is related to the incubation time, not exactly the incubation time. And this W is a so-called Lambert W function, which is basically solving an equation which is partly exponential, partly algebraic. So that's W function comes out of that. So this may look a little bit weird, but it's actually not that different from the standard SCR model. So if you have M exposed compartments and N infectious compartments, you could basically write a similar equation, which you have to solve it implicitly. You cannot solve it explicitly, but there's a similar equation that needs to be satisfied. And the behavior we get here in terms of fitting the data is very similar to what you get from 2 exposed components and 1 infectious component. So this part is actually not that different from the standard CAR. The main thing that we're doing is that we're modeling beta, this infection rate, and the susceptible density in terms of the properties of a county. And by the way, this W, something you notice about it, and again, this is more or less similar with the CAR, is that at large interaction rates, this W becomes logarithmic. So if you have a lot of interactions, the growth rate only logarithmically increases with the density of susceptibles. But if you have few interactions, it becomes linear, and eventually it becomes negative because there is this recovery rate. So if the interaction becomes less often than recovery, then of course you reach what's known as herd immunity, or basically lambda becomes negative. So we're going to come back to that in a minute. So that's the model, and we try to fit it to data. And the model we used here had 9 parameters. The more recent version has slightly fewer, around 11 or so parameters. But basically, we can fit all these 8,000 data points with a reduced chi-squared of, well, the square root of that is 1.14 to 1.3. So what this means is that basically, the fitting errors, the uncertainty model is basically somewhere between 14% to 30% of the measurement errors. And these are the examples of of these fitting models. So the red is what the model gives you. These are basically 6 counties, the highest number of mortality as of, I think, last couple of weeks, total mortality in the US. So Cook County is Chicago. This is Phoenix, Arizona. Then you have Los Angeles, Miami, Detroit, and then New York City, of course. And what you see is that the red seems to be approximately fitting the blue. The blue is actually what happened. Red is the best fit model with these 9 parameters. And of course, there are deviations, but you see the blue region has errors. So that they are consistent with errors up to around 14 to 30%. So effectively, our model does have some systematic errors, but it's a smaller, comparable or smaller than the measurement errors. And in fact, we do study all those errors and include them in our prediction forecast as well. So that's the way it works. So the model has some parameters that tells you how this interaction rate beta depends on social mobility, on the weather, on population sparsity, and there is dependence on total annual death. There is dependence on the total death fraction in the county. This is the issue of herd immunity I'm going to get to. And then there is the incubation time, which we get a large number, but it's not actually the incubation time. This is something that's related to incubation time. So the incubation time we get is somewhat long, but it's not much longer. Maybe it's within a factor of 2 of what others measure from direct studies. So this is the issue of the errors. This is how predictive the model is. Again, these are the same parameters fitting all the US data. So we're not doing independent fits for different places. It's the same parameters that fit the same all the different places. And this is an interesting thing that we have, in fact, this is an important discovery that we made, that you could model herd immunity as an exponential decay of the population of susceptibles as with some free parameter times the number of the death per population, basically total COVID death fraction. And the value of CD that we measured is somewhere between 3,000 and 4,000. So that basically means that if 1 out of 3,000 people die in the community from COVID, then the number of susceptibles decreases by an e-fold, by exponential of 1. So that's the way the model works. And based on that, we can make predictions. Now we have a mechanistic model, and we know what drives the COVID into the future. We have quantified the dependencies on the mobility, weather, and all the various factors. Some are static, some are dynamical. So based on assuming how these things change in the future, and of course you could change that, because that's how we can set policy. And this is why this is important. So this is something that can be used to set the policy, because it does tell you how various measures affect future evolution. You can see what happens. Some counties, so this is Boston on the right, up top right, and Miami on the bottom right. So this is what we were predicting back in July for what's going to happen to them. So our prediction was working over a month period reasonably well. On the left here is Seattle, and this is Los Angeles. So this is how the model evolved. So the predictions, they also changed, because of course, this is what the model is telling you is based on actual mobility. So we don't predict what people do into the future. We just say that if people do this, this is what's going to happen. And this is basically how things evolve from where I showed before, based on the actual mobility of people. So in Washington, Seattle, Washington, things actually went down as they did in Boston. In Miami, of course, they had a huge outbreak, which is still ongoing. I think there's still, maybe it's going down now. And LA, it's basically kind of a steady. I mean, our model was just saying it could fluctuate up and down, but I mean, in fact, it has been a steady more or less. Maybe it's starting to decrease now, depending on what happens. So that's how the model works. And now we have integrated face masks based on data from New York Times and Google Trends. And so this is an example of how, if you use the option of face mask in Los Angeles, what difference it makes. So this would be starting from the end of October. If everybody uses face masks, then the epidemic would decay. If no one uses face masks, then it would it would decay at first, because there is, of course, a delay from when you set this until implementation. And But then basically there could be a second peak, although there is a lot of uncertainty on what might happen. So there are other things that matter for the pandemic. So as I said, there is dependence on face masks. So we have definitive evidence that the pandemic growth rate could basically be decreased by about 0.1 per day if everybody uses with the maximum face mask use. So this is the kind of range of face mask uses that we have seen across our data. And this is great, but this is not enough. So if you remember, the growth rates that you were seeing were somewhere between 0.2 to 0.4. And places that are more densely populated, face masks themselves are not enough to basically mitigate the epidemic, and other things like lockdowns are necessary. So lockdowns are much more effective, but of course, much more restrict than use of face masks. We also have very definitive weather dependence, which is, interestingly, it is not monotonic. It looks like there's an optimum weather around 20 degrees or temperature. If you go to higher temperatures or lower temperatures, the epidemic seems to be growing faster. And possibly the easiest way to understand this is that this is the temperature at which, or around the temperature where people spend most of the time outdoors. At much hotter or much colder temperature, people go indoors where transmission is much more effective. Again, the dependence of this is also very statistically significant. Okay, so since I've been talking to myself for the last 45 minutes, let me ask Elena, so how long more should I go, or Jude?
We have 1 hour for the lecture. So it's 11:15. So we can have maybe 10 minutes for questions or 5 minutes for questions.
Okay, I see. So I can go for 5 to 10 minutes, and then we have a few minutes for questions. Okay.
Yeah, sounds good. Thank you so much.
No problem. Okay, thank you. Okay, so let me just try to wrap up. So one of the most surprising things that came out of this analysis, and we weren't expecting this, and I mean, we are not epidemiologists. My collaborator, Ben Holder, he has some background in virology, but that's far from, I mean, being an expert. So this was the most bizarre thing that we found. So there is this issue of herd immunity, which I hadn't even heard about before. So what's known as classical herd immunity is basically if there are enough people in the population who are immune either through infection or vaccine, then the RFT, reproduction number, falls below 1, which is the same as in our language is lambda becomes negative. But there could be an overshoot that I'm going to tell you about. Now, estimates of when this happens, it could be for COVID, it could be somewhere between 20% to 70% of infection. And the lower values are particularly due to Britton et al. And Gomez et al., who include heterogeneity of infection or infectiousness or being infectious, basically, becoming infected. So the ability of infecting other, ability of becoming infected, if it is very heterogeneous, that number gets lower and lower. But exactly how low it goes, it's a controversial issue. There are various types of immunity that may or may not be permanent, and there's debate as to how long immunity might last. However, what we do have is not a speculative, but just direct measurements of the death fraction, which is much more easily measurable than the infection rates. No, we cannot measure infection in the entire country, but we can measure how many people have died of COVID, at least with a much better precision. It's much more objective and quantifiable probe. So that's what we're actually doing here. And our model, it does find a very significant dependence. All else being equal, there is dependence on the death fraction. And the easiest way to explain it is the herd immunity, basically. The more deaths per population, the more immunity there is because more people are infected, although we don't know exactly how many because we don't measure that. But what we do measure is deaths per population, and the more of them there are, the more people pass away from the disease, unfortunately. The smaller is the susceptible population, and then this does go negative. The growth rates become negative. If you look at the deaths, the daily deaths versus total death, basically you have these trajectories that they all go up, reach a maximum, and then start to come down. Now, these trajectories are not set in stone. It actually does depend on the mobility restrictions. And the peaks, in fact, tend to go lower. And the maximum where you stop, it becomes smaller if there are mitigations. So the lockdowns do work. And our models very definitely show that. So the blue here on the left is a 33% lockdown for a typical US county. On the right is a 42% lockdown for New York City. However, if you don't do the lockdowns at the right time, too late or too little, then you go, basically you can overshoot herd immunity. Now, what is herd immunity? Herd immunity is this green point here. So that's the point that if you are there, the epidemic doesn't grow anymore. Basically, that's the case. But however, if you are up here, if you reach there, the epidemic does continue, even though it's decaying, there's still more people will get infected and more people will die. And this is known as the overshoot. So herd immunity can happen, but if you have unmitigated epidemic, you always overshoot herd immunity and many, many more people would die. So in this example, for a typical US county, without lockdown, you could have 3 times as many as what herd immunity tells you, fatality. In New York City, which is more densely populated, that factor could be much, much higher. And that's the prediction of our model. You could look at this for various US counties, and it turns out, for example, Miami has now overshot its herd immunity threshold. Boston is right around that point. However, LA and Seattle, Washington are far from it, and it's just because of the lockdowns. You see these blue curves have kept them down there, but if the lockdowns are lifted, they will, if they're lifted instantly, then they could overshoot, but if they're lifted gradually, they could reach herd immunity as well. So generically, we find that somewhere between around 80% of the US population remains susceptible or live in countries that are still susceptible. So only around 20%, 20 plus or minus 7% have now reached herd immunity according to the model. And those are places like New York City, Detroit, and New Orleans or Boston, where somewhere between 0.1% to 0.2% of the community have died of, have passed away of COVID. And the denser the place is, the larger is this threshold, but that's the range that you have. So for New York City, for example, it's around 1,700 per million, so it's around 0.17%. For LA, it's more like 0.1%. But the majority of US remains susceptible. So we had this example, so does it actually work? And it turns out that, so this is a prediction. We said that if a county reaches herd immunity, the epidemic cannot grow again. And there won't be a second wave. So one example was New Orleans that has passed herd immunity according to this model. And we found that it should reach, the epidemic shouldn't grow. There was growing cases at some point in New Orleans, but the death never actually grew. So our model, which was predicting it shouldn't be a second wave, that seemed to work. And yeah, there hasn't been a second wave in New Orleans. These are other examples of places that reached herd immunity that even though the cases do seem to grow, maybe for months or even peak, the death never seemed to grow really. So that's, I mean, the predictions seem to have held up, at least on the places that that have reached herd immunity. So let me wrap up, and I know this is a controversial issue. So we think that there's a logical way to manage pandemic. It's by understanding what drives it in your community. By understanding what drives it in your community. And by understanding the various costs of lockdowns or mitigations. So if you understand an epidemic model, what's happening in your community and which of these factors are important for epidemic in your community, and if you understand the cost of the mitigations, and then you also understand the different possibilities of, or the probabilities of outcomes or endpoints, either vaccines or herd immunity, or herd immunity through natural infection or vaccines, you can optimize your strategy. So the most important thing is that you should use scientific evidence rather than politics. And the politics can be very complicated, but what we have here is the science. I'm gonna skip, in the view of time, I'm gonna skip two things. I'm gonna skip this issue of super spreaders versus vulnerables, which we do have some results on. You can ask me about it later. This is obviously a very sticky issue. There are these two competing petitions. There's a great Barrington Declaration and there's the John Snow Memorandum. The first is advocating against lockdowns. The problem with it is that, in fact, if you want to get reach herd immunity, that requires more than 400 deaths in the US, or 15% of annual death, 400,000 deaths. They advocate for protecting the vulnerable, but it's not clear how that should be done. And they advocate for no lockdown, but we show that if you do that, you're going to overshoot the herd immunity threshold by a factor of a few. So this is not, no lockdown is not a very wise herd immunity strategy, even if that's your end goal. The other one is continuing restrictions, but the question is, what is the cost? Is the cost of that greater than that of herd immunity? And we can talk about that if you're interested, or you ask me about it. And then there's a statement that there is no evidence for lasting protective immunity. I think we have very significant statistical evidence for lasting protective immunity, at least for the 6 months that COVID epidemic has been ongoing. So to wrap up, I think we have a pan-epidemic approach to epidemiology. This is complementary to other approaches. I think we have community-specific, or we advocate for community-specific epidemic interventions that depends on specific properties of the community. Herd immunity, we think, can happen, although in most places it has not. And the counties are not islands, so we have to actually do more special. So herd immunity is not really localized. So in principle, the story can be much more complicated if the herd immunity is reached in one place, not just in its neighbors. So that also have to be understood, and that's for the future basically work. So evidence for immunity is decisive, but it doesn't last. We can now address this given the length of the US epidemic and worldwide epidemic. We want to extend this to Canada and other countries, but we need local expertise in epidemiology. So this is why I'm desperately hope we can recruit more people to work on this. We are not epidemiologists by training, and we have our day jobs as well. What are the best ways to track social distancing? So that's a question to be addressed. How to balance harms that due to COVID against those of lockdowns on mental health, economies, etc. And I want to end by saying that we are all in this together. So let's work together to solve this pandemic and basically help each other. Thank you.
Thank you so much for your amazing talk. Thank you.
Thank you.
I think we can go with the questions. And actually, we already have one in the chat. Okay. So I'm going to read from Di Sheng. Mm-hmm. When we feed for COVID-19 mortality data, should we alter disease-induced death rate? And if so, what is the general principle to guide this change?
I don't think I understand that question. So we only use the reported COVID-19 mortality. So that's the death that we are looking at. Now there are always some missing deaths that can actually complicate our analysis, and we haven't really looked at how much missing death would affect the result. But that certainly could be a systematic error that we're making. I don't know if I answered the question, but yeah, maybe you can ask again.
Thank you. We can, if Ji Cheng wants to clarify. Oh, sorry, Jude. Mm-hmm.
Yeah, go on. He can follow up on you after the talk.
Yeah.
That would be great. So we'll share your email and other information. Elena?
Yeah, I was about to say the same thing. Thank you. So we have a question from Yi saying, thank you for the lecture. How are mobility, humidity, population sparsity, and related to beta? And is beta a linear function of these factors?
That's an excellent question. And in fact, a priori, we don't know. So what we assume is that the logarithm of beta is linear in these factors. So that's obviously an assumption. We did try the dependence, nonlinear dependence. And for example, for the weather, we did find a quadratic dependence. With other factors like social mobility or population sparsity, the dependence, we didn't find any higher order dependence. That it's not that it's not there, but it's just that maybe the data is not good enough to find those higher order dependencies. But yes, that's an excellent question. And so far, we just start with linear regression of logarithm of beta, and we only add higher order corrections where it's necessary.
Thank you. And I actually have two questions. So
Sure.
for the, regarding your data, so for your correlation, I'm not sure if you can get data from Europe, but since what's going on, with this definitely second wave going on right now, are you expecting that you will get the same correlations depending on the density, or maybe the density because in Europe is definitely different from the one in North America, given the population and so are you expecting the same correlation, or maybe from Europe you will expect something, something maybe can be more correlated respect to the other ones?
Yeah, that's an excellent question, and we don't really have as detailed the data right now with Europe. At the country level, we kind of have done this exercise, but that's a much coarser analysis, and we find similar dependencies between Europe and the US, but we don't have the detailed country level information for Europe yet. So yeah, I think the problem is that in particular, this mobility information that Google provides, it's country specific, and it needs to be calibrated for every country. Because like what people call grocery stores maybe in China is not really the same as what they call grocery stores in North America, at least according to Google. I mean, just giving that as an example. But yeah, I mean, I expect a similar thing, and most of Europe, similar to the US, hasn't actually reached herd immunity according to these thresholds. So there might be isolated pockets that has reached it, but yeah, so that this will happen, and it needs to be modeled properly.
Okay. And my second question is actually on your model, on the SCIR model, because we know that for COVID-19, a big question is the transmission from asymptomatic cases. I know there is no data on that. It would be very hard to get data on the asymptomatic cases and their transmission, but are you planning to somehow extend your work, including transmission from the asymptomatic cases? And if so, how are you trying to model them?
That's an excellent question. So kind of our approach has been try to, now we can add this as extra compartments, but our approach has been just kind of to calibrate this against the data. And the data that we are using is the mortality growth rate, because of course, the positive cases, there are a lot of missing cases, and asymptomatics, most of them are missing probably. So we're not actually using the case information, we're just using mortality as an indicator or proxy of the growth rate. And then we see basically, does it fit the data? So can the information that we have based on mobility and various local conditions, can it predict correctly the growth rate? So that has been our approach. And so this kind of decoupled our analysis from the case detection. Although that will also, I mean, I think that will matter at some level, but it's just such a much harder problem because every local community has their own policies for tests and things like that. So modeling that is I think harder than modeling COVID itself. Yeah.
Okay. Yeah, I understand that even the mortality from the asymptomatic cases might be hard to detect.
Yeah. So we just look at the mortality for our analysis, but yeah.
And then we have another question by Saye saying, does your model distinguish between different types of mobility, for example, flights or local mobility?
Good. So the type of mobility that's publicly available to us, and this is something that policymakers can actually make a big impact because, of course, there could be much more data that becomes publicly available. The data that we have is one that's been released by Google, And it says basically how many people go to, say, grocery stores, to restaurants, to workplaces, compared to their normal level of activity back in January. So it doesn't actually tell you where people go from. I mean, it doesn't actually give you, I mean, this location going from one place to another. It just tells you the level of presence in various places. And that's the only data we have available. It turns out that for community transmission, that seems like the most relevant thing. I mean, for the onset of the disease, of course, the flights would be important. But since, I mean, a small fraction of the population actually participate in flights, then I don't think that's a big contributor to the community transmission. And the onset is, of course, the hardest thing to always predict because it's such a stochastic process. So yeah, so we don't have access to that data, and that's why we focus on community transmission in places that, in local places that people do it, basically.
Niayesh, thank you so much for the great talk. I know we're running out of time. Let me just ask you a short question. We could discuss now. I'm curious to know, given the non-linearity that you realize between some of the cover rates and the growth rates, why choose to use a linear model instead of something like a generalized additive model that will be able to capture some of the non-linearity that are involved? And secondly, my question was supposed to be twofold. What expertise, we have a lot of people listening to us here.
Yes.
CDM has a lot of network. So what expertise do you need to be able to apply this to Canadian provinces to be able to predict the growth rate of COVID as we expect? No, we don't expect that, but as subsequently other waves may come up.
Yeah, those are excellent questions. So I think the reason we started with the linear model was that it's a much more easier fit. As you know, if you try to fit a linear model, there's always, I mean, one fit, basically. There's a simple way of doing it. Now, linear models, the problem with it is that it's just much more time consuming to make that work. That's why this was our strategy, because of course there are many covariates that exist in real world, and trying to kind of, if you want to quickly go through all possibilities, doing the linear model is just the faster strategy. I mean, ideally, the nonlinear, you want to do everything with the nonlinear model if you believe the nonlinear model. The other problem is that, of course, your nonlinear model might be wrong. So linear model, at least it's one thing. It's everybody understands it, and we don't have to. It's model independent. Now, to ask your second question, that's an excellent question, both for Canada and across the board. So I think the kind of the data that we need is all this kind of very localized information that some might be available publicly, but some of them are not that easy to find. So local demographics, all the basically localized COVID data, which, I mean, I know they are publicly available in different places, but they need to be put together. The mobility data, like for example, one of the issues that we have is the Canadian health districts, as far as I know, don't quite match the Google's districts. In US, there is one definition of county, but in Canada, there are various definitions of its districts. So I don't think, so that's one place that we have trouble matching these. So someone who has expertise in this, and in general in data science, can help us, because all we're doing, I mean, of course, epidemiology. What we want is, we want to do epidemiology, but we want to bring as much data as possible into it. And these are data that are coming from government sources and not non-government sources, maybe cell phone companies. If they could contribute to it, that would also be very useful, because the more information we have on mobility, the more we can basically do with it, right?
Thank you so much again. Thank you so much for listening. Before I end, I just want to say that the CDM is part of the Canadian COVID-19 task force, and there are a lot of people listening to us right now that have access to the data they are talking about. They will be reaching out to you, and please, if you did listen to our great speaker today and you have access to the data that he's talking about and you want to collaborate, please do reach out to him or reach out to CDM, and we'll connect you to him. Again, thank you for the great talk, my friend. You did a great job, and I'm proud that you kept aside what you had to do and put your efforts together with every other researcher in the country to see that we get rid of this monster. I'm proud of you. You're a patriotic citizen, and I'm glad of what you're doing. And that is what a lot of citizens are doing right now. Thank you so much. Thank you for coming.
Thank you very much. We are in this together, and I hope we can work together. Okay. Take care.
Thank you. Thank you.
Thanks, Elena. Thank you. Bye-bye.
Thank you. Bye-bye.
Okay.